Hello, calculus students and general seekers of truth. Welcome to the series of videos on Taylor Polynomials, and I think this is our fifth or sixth video. And at this point, I make this note here called errors and hand waving, because it's important to understand the scope, the power, but also the limitation of our methods here. So what we've been doing all along is using G to approximate F. Okay, so you're given some function f, like the sine or the cosine or anything else, and you want to use a polynomial g in order to approximate, and you have this. But note that g and f are only close. They are not perfectly equal. Okay, so they are not equal. This is still only an approximation. Okay. In other words, we can think about it this way. We can think about it in terms of g of x, or I'm sorry, I'm going to write it this way, is that f of x is equal to g of x, okay, plus some error. Okay. So they're not perfectly equal. They're equal to each other, plus or minus some error. In other words, f of x is equal to this expansion, f of a plus f prime of a x minus a plus f double prime of a x minus a squared all over 2 plus dot 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 plus some error. Okay, and at the first video in this series, I talked about how we're going to approach this from a couple different standpoints, and we're not going to get too rigorous here. We got into some quite a little bit of detail, but as far as AP Calculus is concerned, we're going to stop at this point in terms of dealing with the error. So here's the hand waving, right? This is what mathematicians usually do when they don't know or they can't quite explain something, or they prefer not to explain it at this point. So the hand waving part comes in, and it says here that, it has been proven that for many functions, the error will approach 0 as the number of terms approaches infinity. Okay. So it has been proven that for many functions, and I emphasize many here because not all functions, you can't do this with every function, but for many functions, as the number of terms approaches infinity, the error approaches 0. So remember back here when we said you want more accuracy, you calculate more terms. Well, it turns out for many functions, if you calculate an infinite number of terms, then f of x would in fact be exactly equal to g of x. Okay, so f of x would be exactly equal to g of x. Remember, this is the formula for g of x. The kth derivative of f at a times x minus a to the kth power divided by k factorial. It would be equal to this as long as the number of terms goes towards infinity. Okay. So this says something quite powerful, that for many functions, including the sine function, the cosine function, and the exponential functions, that you can rewrite them, an equivalent version of them, as an infinitely long polynomial. Okay. But I want to emphasize that this only works for some functions, and this is a bit of hand waving. There is, if you will prove this if you are a math major. If you decide to become a math major and major in this, at some point, hopefully, one of your professors will prove this to you and ask you to, and probably require you to understand and do the proof yourself. Okay, so I want to make that emphasis here. But as far as we're concerned, I'll show you the functions that apply to this, and we can do some powerful things with that, even without having to do a proof. The next thing I want to make a note of here is that something about that special point, x equals a. We use pi over 6 in our example, but it can be anything. So a can be any point for which f of a is known, and known exactly. Okay? So a, I guess I'll try to italicize this a little bit. A, can be any point for which f of a is known exactly. For convenience, we often use 0. Okay? And I'll show you how the sine function is used in that way. So let's see here. Let's apply what we know so far about the sine function. Okay? And using x equals 0, I'm sorry. X equals 0 as our special point. Okay, as our special point. So the Taylor series says that this is the summation from 0 f k of 0 times x minus 0, which is just x raised to the kth power, all of this divided by k factorial. Okay. And just a quick note here, I'm going to do this on the side. So if you have sine here as the function, then the first derivative would be the cosine function, then the second derivative would be the negative sine function, then the fourth derivative would be the negative cosine function, and then the fifth derivative, we're back to where we started from. So this would be like the, let me think about it this way, the 0th derivative. This is the first, this is the second, this is the third derivative, okay? And then the fourth derivative and onwards, we're back to where we started from. Okay, so let's see what happens when we expand this out. So the 0th, when k equals 0, the 0th derivative is just f of 0, or sine of 0, times x to the 0 divided by 0 factorial, plus the first derivative, okay, of x to the first power over 1 factorial, plus the second derivative at 0 of x to the second power over 2 factorial, plus the third derivative, I'm going to write on the next line here, the third derivative at 0 of x to the third divided by 3 factorial. And I'll go one more, the fourth derivative, 0 x to the fourth divided by 4 factorial. Okay? And let's see what happens when we apply these results. Well, f of 0 is just 0. So I'll write it out too. This is sine of 0, x to the 0 over 0, plus cosine of 0, x to the first over 1, plus negative sine of 0, x squared over 2 factorial, plus the third derivative, which is negative cosine of 0, x to the third over 3 factorial, plus the fourth derivative, which is back to sine again, of 0, x to the fourth over 4 factorial. Okay. And sine to the 0th is just 0. So these are all gone. Okay. And then cosine to the 0th, cosine of 0 is just 1. So what we have left here is x minus x cubed 3 factorial. And the next term here is going to be plus x to the fifth 5 factorial minus x to the 7th 7 factorial, and so on. In other words, all the odd powers. So the signs are alternating, and then the powers here are just all the odd ones. X to the first, x to the third, x to the fifth, x to the 7th, and so on. Okay. Now I'm going to continue and show you what happens to cosine. So applying what we know here, this is the first derivative, the original cosine function at 0 times x to the 0 over 0 factorial, plus the derivative of cosine at 0 times x to the first over 1 factorial plus the second derivative of cosine, which is just negative cosine, times x squared over 2 factorial, plus the third derivative of cosine, which is just sine of 0 x cubed over 3 factorial, plus the fourth derivative of cosine, which is back to itself again, of 0 times x to the fourth over 4 factorial, plus the fifth derivative of cosine at 0 times x to the fifth over 5 factorial, and so on. Well, let's do what we did last time again. So the sine functions are going to cancel and destroy all of the odd powers this time. And what you have left here, that's just 1. Okay, this is just 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. And this pattern is going to continue. It's going to be negative x to the 6 over 6 factorial plus x to the 8th over 8 factorial, and so on. Okay. So if we use, so this is actually what the cosine function is equal to. Just an infinitely long polynomial of alternating signs and of only all the odd powers of x. Okay, so here's, you learn somewhere along the way that cosine is even and sine is odd. Well, here's another way to remember it. Well, thank you for watching and have a wonderful day. Be sure to keep on watching the next set of videos when I talk about the practical and theoretical implications. Have a wonderful day.